Okay, in Unit 8, we're going to talk about planning and how planning works, in particular focus on something called Markov decision processes and how MDPs can be used to plot out decisions. Um, we're going to look at two units in the Stanford video series. Unit 8 introduces planning, and Unit 9 introduces planning under uncertainty. So let's start with this unit on planning. This is the list here.
Hi, and welcome back.
So Peter Norvig's going to introduce this concept with planning. Let's just listen to him for a sec.
This unit is about planning. We defined AI to be the study and process of finding appropriate actions for an agent. So in some sense, planning is really the core of all of AI.
So listen to Peter. He goes over and talks a little bit about the difference between planning and problem solving. Problem solving is when we know everything ahead of time. So like with A star, if we know all the possible routes, we can calculate the shortest distance. That's problem solving. But planning is used more like when we're trying to find a route and there might be traffic there and we don't know where traffic is all the time. And so we work on different situations to do planning. He introduces a vacuum cleaner problem here.
Here's a state space diagram for a simple problem. It involves a room with two locations. The left we call A and the right we call B. And in that environment, there's a vacuum cleaner, and there may or may not be dirt in either of the two locations. And so that gives us 8 total states. Dirt is here or not, and the vacuum cleaner is here or here. So that's 2 times 2 times 2 is 8 possible states. And I'm drawing here the state space diagram with all the transitions for the 3 possible actions. And the actions are moving right, so we go from this state to this state, moving left, go from this state to this state, and sucking up dirt, we go from this state to this state, for example.
So he introduces this state space, and this is very common in some planning, is to try to break the continuous world into a set of discrete states that we can work with, and talks about this issue and something with partially observable vacuum cleaners and mapping this onto what is called a belief space, and that's
This is the belief state space.
a diagram of where you could possibly be. So here we look at all the possible states we could be in, and then if we move right, what possible states we could be in. And this is interesting. AI often does this is try to make a more abstract view of things and reason about this more abstract view. So he goes over this, but we're not going to go into too much detail in this because we're going to focus on the next thing, which is planning with uncertainty. So he does introduce classical planning here and some of the techniques with classical planning. And here they're talking about like flying planes. And again, this is a classical planning thing where we have this logical inference where we say we have a plane at some location and we have cargo at some location and all this stuff, and we try to infer this sort of stuff. But again, we're going to not dwell too much on this, and what he introduces is situational calculus here. So instead, we're going to focus more on this planning under uncertainty. So we're going to go into Unit 9 of the Stanford course.
Today is an exciting day. We'll talk about planning and uncertainty.
And Sebastian is excited about this unit. Surprise, surprise. So he introduces this unit and talks about this grid world and introduces this grid world.
Planning under uncertainty.
I'm sorry.
In this
This talks about the basics here. He also gives a tour of how this has been used on a number of the robots he's created over time. It's interesting, but not critical to the class. Here's where he introduces grid world, is in the 4th one.
Let me give a much simpler example, often called grid world for MDPs. And I'll be using this insanely simple example over here throughout this class. Let's assume we have a starting state over here, and there's 2 goal states, or often called absorbing states, with a very different reward or payout, plus 100 for the state over here, minus 100 for the state over here. And our agent is able to move about the environment, and when it reaches one of those 2 states, the game is over.
Okay, so this is our grid world we'll be working with, and we'll be working this in this assignment and stuff. So he walks you through the basic idea of grid world and some ideas of this.
Let's look at the grid world again, and let me ask you a question. I wish to find a optimal policy for all these states that with maximum probability leads me to the absorbing state plus 100.
Okay, so we talk about this policy and trying to find what direction you should be moving at any location on the grid given the current conditions. We also talk about some cost things and something called value iteration, and this is what we're going to be looking at in this
The
assignment.
definition of the expected sum of future possibly discounted reward that it has given you allows me to define a value function. For each state S, my value of the state is the expected sum of future discounted reward, provided that I start in state S, then I execute policy pi.
Now, this is a pretty complicated expression, so we'll look at a couple simplified versions of it in this world. First, he walks you through this deterministic area, and then finally we get to a stochastic area where we don't always know where we're moving to. So
let me ask the same question for the stochastic case. So we have the same word as before, and actions have stochastic outcomes. With probability 0.8, we get the action we commanded, otherwise we get a left or right.
So in this world, if we're trying to move in a direction, 80% of the time we'll get to that direction, but 10% of the time we'll end up left or right of that direction. The idea is that we might be working with a robot or some sort of AI unit, and it doesn't always know which way it's facing very well. So when we say go forward, 80% of the time it'll go where we think it will, but 10% of the time it'll end up to the left or to the right of that. And then here's this new equation. He simplified it some. So we look at our 4 actions and we try to maximize the different costs. So we look at all 4 equations and find whichever one gives us the highest value. And this is how we calculate each value. For each value, we sum up the different end goals will end up at the end states we can end up for. So, and then each one we multiply the probability of ending up in that state times the value of that state, and we do that for all the possible states we'll end up for that move. And then we add on a step cost. Often there's some cost of just taking a step that we add on here. Now this is kind of hard to understand, so I've simplified it a little bit more and put it in a little bit more of, I would say, computer science terms. So we're calculating some new value, and we're going to sum up all the, we're going to look at all the states we could get at for this move. So each S is a state that we could end up with, and we're going to look at the probability of the state times the value that's currently in that state, and we're going to sum that up for all the different states we could get at, and then finally we're going to add in our step cost. We're going to do that. We're going to calculate this step cost, this new value for each of our 4 moves, up, down, left, right, and then we're going to pick the maximum of those. Now it's still probably confusing, so let's try to walk through an example of this. Here's a different grid world that we have, and some values we have filled in, and we're going to try to figure out the value, update the value here at this cell, which has a 20 value right now. Now we're going to assume that we have a 80% chance of successful move. So if we, like here, and we're trying to move up, 80% chance we'll be there. If we try to move up, 10% of chance we'll end up moving straight to the right, and then 10% of chance we'll end up moving straight to the left. Now if we hit a wall, an exterior wall or an interior wall like this, we bounce off and end up back where we started. So actually it's 10% chance we hit this wall and bounce back and end up here. Okay, so we have our 4 moves: move up, right, down, left, and we're going to calculate a new value. So we're going to use this equation to calculate a new value for each one of these. So the probability of each state times the value of each state, and sum those all up. So from here, if we try to go up, 80% of the time we will get up. So we have 0.8 times 50, which is the value when we get there. Now 10% of the time we're trying to go up, but we'll end up over here because we're not oriented right. So 10% of the time we'll end up at 40. So 10% times 40. And 10% will accidentally go this way, we'll bump into this wall and end up back here. So 10% of the time we'll end up at a 20. Now, no matter which way we go, we have to pay the cost, the fuel cost, the step cost, and that's 5. In this case, the step cost is 5. So we calculate this out and we end up with 53. So this is a new value if we try to go up. But we don't know if that's the best move. What if we go right? So if we go right, let's look at that. 80% chance we'll end up with a 40 cell. 10% of the chance we'll end up down here at -1. And 10% of the time we'll end up at 50. So we take that, and then again, we always have the step cost if it's non-zero. And so we can calculate that. Now that ends up with a -13. So going this way is not very good, because there, even though we're going this way, there is a slight chance we'll end up back at this very bad cell down here. So similar, if we move down, 80% chance we'll end up at this -100, 10% chance we'll end up bouncing off this wall and back here at 20, and 10% chance we'll end up at this 40. So that's our calculation. And then we add in our step cost. If we move to the left, 80% chance we'll bump into this wall and end up back at 20. 10% chance we weren't oriented right and we end up here, and 10% chance we end up down here. So this is our 10 times 50 and 10 times 100. This is our calculations. So we've calculated the values for each of our moves. So if we run this calculation, this is what we get for each of these moves. And now what we want to do is we want to find the maximum of all the possible moves. So which one of these is largest? Well, most of them are negative. This is the largest, 53. So we would update this with 53. And we'd also keep track of the policies that the highest move was going up at this point. So we'd remember going up is what we had to do to get that policy. So you should be familiar enough with this equation so that you can update these policies. If I give you on a future quiz, give you something like this and ask you to update a grid cell, you should be able to do that. So take enough notes so make sure you'll do that, be able to do that in the future. Okay, we're going to then look at this in Java and some Java code in this assignment. So there'll be another video here that'll walk you through the Java code for this and running through this cost. So that's all we do. There's no participation activities this week. There will be an area where you can post questions. They're not required. We're trying to limit interactivity and requirements because, again, you'll be doing a quiz this week for this. So this is a quick introduction to Markov decision policies. These are really interesting policies that are, again, help us map out how to do activities. Now, one final thing, Sebastian does go on and talk about partially observable versions of these. We're going to skip all this. So we just want to be able to understand this value iteration with this stochastic Markov decision process. Okay, hope you enjoyed the unit.